What's up, Joe?
Hey, Adam.
Good to see you, buddy. Thanks for making the trip out here.
Oh, my pleasure. Thanks for having me.
Absolutely. How you liking Tehachapi so far?
Love Tehachapi. It's good to be back. I was trying to figure out the last time I was here, but it's been a minute.
It's been a minute, but you've been here before
Several times.
several times. I thought so.
Yeah.
Right. All right. It's grown probably since you've been here.
Yeah, a lot's changed.
More renewable companies,
Yes.
which is
Yes.
great.
And more food options.
More food
Yeah,
options.
coffee shops.
We do. Yeah. We're growing up. It's getting fancy.
I love it.
Yeah. No, that's good. Well, fantastic. I'm glad you came out to do the podcast with us and travel went well. So tell us, what is going on with Padge Engineering?
Oh, a lot's going on with Padge Engineering. We have about 5 very good clients in the solar and wind space, mostly in the solar space. We're helping them solve some of their biggest challenges, systemic fleet challenges, and helping them operate to be where they want to be, or where they want to be.
That's close to your slogan.
Yes.
Making wind and solar all we know it can be.
Yes. We all love it, and we all want it to be
Yeah.
at a certain point. So, my goal, and everybody that works with me and all of my customers is to do that.
Right. And we need you finding those problems, but more importantly, finding the solutions to them.
Yes.
Right.
Yes.
Yep. I love it. And I think I just talked to you a few months ago. You were out in the West. You get around several states.
Yeah.
Hodges.
I'm like Johnny Cash. I've been everywhere. At least I feel that way.
Right.
I got a lot of frequent flyer miles this year. So yeah, I do get around a lot.
High demand.
High demand. Yeah.
High demand. Obviously, that's because you're great at what you do, but, well, that's the supply piece. But why is the demand high?
That's a very good question. The demand is high because renewables is just exploding. Adam and I, we worked together at a company for many, many years, and that company mostly specialized in wind. And we saw an explosion of wind. I mean, we're here in Tehachapi. It's the birthplace of wind in the U.S. Solar's going through that now. If you were to liken the industry to like the growth of a person, we're not in infancy in solar, and many people think that the industry is very mature because we've been putting them on rooftops for years. But that's a different voltage, a different scale. Now you're talking tens of thousands of panels, hundreds of inverters, all spread off over acres. It's a lot. It's a big deal on the operation and maintenance side. So that's the demand side. I appreciate your words on the supply side. That means a lot to me, so thank you.
Yeah. So it's but the demand specifically for Podge is not just the operations piece, but improving reliability.
Yes.
I assume is the focus.
Yeah, that's one of my biggest focuses is helping customers get their assets to where they want them to be. So sometimes there's little quirks here, little quirks there, and we come in and we help them to make that improvement. So we do specialized engineered solutions, really. So
Specialized. So it's going to be tailored to the component type, manufacturer, platform, location.
yes, they're all different.
Yeah.
There's probably at least I can name half a dozen solar inverter OEMs, and they all do them differently. For instance, with respect to IGBTs, some people might do an H-bridge topology. Some people might do a 3-level diode clamp multi-level inverter. So you got these different topologies, and the way they cool them and the way they arrange them, it's all different. So each solution, if there is a problem or if we're trying to increase the output, it's customized to that.
Okay. Well, we got the electrical engineer here, so you're going to have to define a few of the words that you just went over.
Sure.
What's the H-bridge? Explain that one.
Well, an H-bridge is more of a traditional type of IGBT arrangement for pulse width modulation. So pulse width modulation is where you take an IGBT or a MOSFET or any type of switching device where you modulate, in the case of a IGBT, you modulate the gate such that the collector and emitter conduct or not conduct, okay? And as you do that at different frequencies, you're able to take your voltage, DC voltage usually for solar, and convert it into something, that's AC, 50 hertz or 60 hertz. So I just mentioned H-bridge because that's an older, more robust style. These days I see most people doing 3-level diode clamped power inversion or power conversion.
How does that work?
If we wanted to get into the nitty-gritty details, we could. But basically,
it's newer technology.
It's not that much newer.
Okay.
So on that side, what you want to do is you want to derive a common point on your DC side. So you'll have a positive, a negative, and then you'll have a common point. And then that common point, some people call common points neutrals or references, and they all carry different names, right?
Yeah.
So that you will take 6 IGBTs, and then one of the IGBTs, they all have a diode inside them. So that's where the diode clamp comes in. I'm not going to draw it out and arrange it, but it's something you can just type in Google, and there's tons of YouTube videos you can watch on it.
Okay, but utility solar power plants are using one or the other, but you see them both being used today still.
Yes.
So there must be some pros and cons in how it's you decide during the development which way you're going to go with your power plant.
There are. I don't get too much into the pros and cons. I mean, in solar, you have things like maximum power point tracking and things like that are important for, like, solar and wind are very similar in many respects, okay? And wind, you're going to take it from AC to DC and back to AC. And solar, you're just going to take it from DC to AC. But you have a large mass of rotating energy.
Right.
And wind, you also have to do something with. So there's special circuitry that's involved there, brake choppers, crowbars, things like that, where solar doesn't necessarily have those, right? So you're just changing your operating point on your VI curve, really, for solar, right?
Yeah. All right, we're gonna get into power conversion a little bit later, I think. But you made a couple of comments. Maybe want to ask what was the startup story of Padge? How did you decide to launch Padge?
Yeah, sir. So first of all, thanks for pronouncing it Padge. It's spelled Padge, but often gets pronounced Padge,
Right.
And that's fine. But it's short for Padre, which is what my kids call me. And now I have grandchildren, believe it or not. But it was originally started as a company to sell online retail, oddly enough. Yeah.
Okay.
Yeah. We were selling on Amazon, and Amazon. This was during the year 2020, and you know what that year was like.
Sure.
So it looked like a good business model to sell. We sold Erica palm plates.
Okay.
Under the name Padge. We've gotten out of that business, so I just took the name, and in October 2 years ago, started doing only engineering, so exclusively engineering. So I've been trying to, in very strategic states, get my professional engineering license. So I just got Texas. So
Congrats.
Thank you.
Those are not easy.
No, they're not easy. But each one has their own, there's a lot of commonality between them, but each one has their own requirements. Like Texas required me to do fingerprints for some reason.
They're going to find you. Yeah. Okay. Well, all right. You're Padre.
I am Padre.
You're
I am he.
Padre. That's right. And whatever business you're working in, I think is always going to be called Padge then.
I think so.
Yeah.
I think so. Yes.
That's where you're working today. I love it. No, that's fantastic. Did you say October of last year?
The year before last.
Oh, the year before
So
last.
coming up on 2 years, just focused on engineering.
Coming up on
October
2 years.
14th is when we incorporated.
Very cool.
2022.
And how was the startup? Did you find people were very receptive? You were able to find the demand?
Yes.
Yeah.
Yes. Demand is not the problem.
Yeah.
It's supply. So I'm having to reach out to, I hire people short time to help me. A lot of mechanical engineers. Electronics is one thing. Keeping them cool, no pun intended, is the harder part. So oddly enough, in the realm of electrical engineering, thermal management is one of the biggest pieces. So I am not the world's best thermal engineer, so I rely on other people to help me do those analysis. And I do sanity checks, comparing the current going through the collector and emitter, looking at the voltage drop across that, making sure the watts dissipated across the cold plate and everything line up with what we're trying to cool. Yeah, so
you focus on measuring the result from the correct temperature control.
Yes.
Yeah.
So have you ever heard the term DOE, design of experiments?
Yeah.
So if we do a customized solution, we try to conduct it such that we change one, no more than two things at a time, and verify that what we're doing actually makes an impact. So if we're trying to reduce the junction temperature of an IGBT, we're going to do things in a controlled environment that we only change one, no more than two things at a time, and measure it.
Yeah. I love this. I know this well, but tell us, why is it so important to change one thing at a time?
Because your combinations or permutations that you put in place go up exponentially the more things you change.
Yeah.
So you really only want to focus on one thing at a time. And then if you want to change a second thing or a third thing, then you have interactions. So you have a multifactorial type design where you want to look at your interactions and see how they play.
No.
But you can't do that unless you do one thing at a time. And then if you do two things, you're looking at three things, 1, 2, and the combination.
No, it's so important. I had to learn that the hard way pretty young. Doesn't matter how smart you are, what you think you know, you can only solve one at a time.
Yes.
Yeah.
You're correct.
Yeah. No, that's a good discipline for sure. Let's thank our friends over at Renew Safety, your proactive partner in safety solutions. With comprehensive safety consulting, ensuring compliance with all safety regulations and standards. Expert staffing solutions, providing trained safety professionals tailored to your project's needs. Commitment to sustainability, promoting a safe and sustainable working environment. Contact Renew Safety at info@renewsafety.com and speak to one of their industry experts about their proven track record for safety management on numerous projects. Or perhaps you're looking for construction safety staffing, contractor monitoring, incident investigation, or program development and training. Check out Renew Safety at renewsafety.com. So almost 2 years, almost 2-year anniversary, another 6 weeks or so, maybe a little more, 2 months. And what's next for Padge then?
What's next for Padge is I want to keep these 5 customers. I want to make significant impacts for them. I believe in them. If they're listening, they know who they are. I want to devote as much as my time to them, making sure that they are, adhering to our tagline, making wind and solar all that we know it can be. So for the next 1 to 2 years, that's where I want the focus to be. After that, we'll see about picking up, another customer, but it's more about these longer term relationships for me. I don't want to do something that I can't stand behind and sleep at night, right? Some people can get on my pillow and sleep just fine at night, but for me, it requires making sure that during the day I do what I need to do to make sure customers are happy.
No, that's, I guess I heard a couple of things. Yes, the 5 customers, you know who you are happy. Yeah. You're expressing that loyalty. There's another piece of passion that seems to come out. Is it for the power type? Is it for the industry? you have this passion making it all that we know it can be.
Mm-hmm.
And I'm sure you have passion for the customers, but is there motivation on just really giving the power plant its focus? Is there something about the technology driving you?
Uh, yes. I geek out a lot on the technology. And so I would say yes, the technology is enticing.
Yeah.
So whenever somebody brings up a new solar inverter that I haven't seen before, I get very excited. It's like, oh, a new one, or a new model from the same OEM. Um,
I love hearing that. I hear it from all job types. So not just engineers, but also technicians,
mm-hmm.
right? I think that's probably the next one, or in a tie. Very excited when they get to observe and work with and learn a new type, a new component, perhaps a new platform, a new OEM enters the space. Yeah, these are exciting times.
They are, and it's going 100 miles an hour right now.
More OEMs than I could keep track of in the last year.
Yes.
And I keep hearing about new ones.
Yes, yeah. Whereas in the wind space, you saw a consolidation of OEMs. In the solar space, it's the exact opposite.
Right.
I hear about others coming into play who may have formerly been in play. So it is an exciting time for solar with that respect.
Now, I met with somebody earlier this week, and they were talking about how some have already left the space. So some OEMs came in, product launch, develop, it's producing, and then they leave the space for one reason or another. This offers another challenge or demand for probably some additional engineering services to keep them running.
Yes, obsolescence is a huge issue. There have been people who've come and gone and left behind a product. Now, that doesn't mean there aren't people who understand the technology and continue to work it. Most of the time, an OEM who stepped away sold the technology to somebody else who also has it. But sometimes they split it up into pieces. They'll sell this piece or that piece, but not the whole thing. So I do have some customer focus on that type of business, continued support for what you would call obsolete from the original equipment manufacturer, but the new OEM has the rights to refurbish or replace that hardware.
Okay, well that's reassuring. So there's it's sitting somewhere, the knowledge.
Yes.
Yeah.
Most of the time it is. It's hard to get at.
I bet.
This industry, everything is hard to get at. And it's meant to be that way. It's a lot of competition.
Yeah. Competition. People are working together in new ways as well. I've witnessed competitors in the same space supporting each other in a lot of great ways. Maybe it's not all types of products and services are experiencing that, but widely.
I think that's good. I think collaborative efforts are good. From my perspective, I don't see that though.
Okay.
Not that much. At the engineering level, most
Protected.
of that's extremely protected.
Yeah.
And I understand the reasons why, and I can't say I blame people for doing that because you're very close to, call it the secret sauce, if you will, at that point.
Sure. Now, we understand people and companies have to protect their patents and IP and, what their secret sauce is, as you said. And then it ages out past a warranty, or the OEM is sold or pieced off, and the owner, operator, is sitting with new opportunities.
Yes.
Yeah.
Yes.
And this is where you come in quite often.
Yeah, you hit the nail on the head. When that warranty expires, that's usually where somebody like me, my company, can help a lot. Because right now the industry is solar especially, is very tied to OEM warranties, whether it's the panels or the combiner boxes or the inverters. They're
Yeah.
all very much tied to warranty claims. Um, and it's amazing that the OEMs can support that and keep a sound business model. To me, that lets you know just how much demand there is, right?
Plenty of demand.
Yeah,
And it's great that they are. And
Mhm.
and they have to keep growing.
absolutely.
And they want to.
They do.
Yeah. They don't want any issues out
They-
in the power plants either.
They do. And I get to speak with a lot of the OEMs too. I mean, many are, well, they're all overseas from a U.S. perspective.
Solar, yeah.
For solar, yeah. But they usually have U.S. Application engineers, but the design engineers are going to be in Japan or China or Spain or Italy, places like that, Germany.
Yeah. Well, we worked for a very large OEM, and my time there was never a day we weren't trying to make that product better. So as they're all struggling through this now because of the growth, right? I think I don't know how I say it. Maybe you tell me if you agree or not, but the citizens of the planet seem to put this demand on more renewable power. Well, more power in general.
Yes.
And so now we have all these great people and companies ramping up to solve for what the citizens want.
Oh, yeah.
Does that sound about?
Yeah. Well, it might not just be citizens. It might be artificial intelligence too.
Oh, okay.
The computational energy required for these new data centers is astronomical. So the demand for energy over the next 10 years are Bitcoin miners, things like that. They consume massive amounts of power.
Right. Forgot about that.
Yeah. And I just don't do wind and solar. I have a project right now I'm doing in dairy. Astronomical power needs.
It's on a dairy farm.
Oh my gosh, yes.
Okay.
Huge.
A lot of moving equipment.
A lot of moving equipment, very sophisticated, most state-of-the-art things I've ever seen. Variable frequency drives everywhere just to control
Well, those do suck
temperature.
down the juice.
Yes,
Yeah.
exactly. So when you introduce harmonics onto the utilities and things like that, you have all types of other issues. So we solve one problem, then we make another one that has to be solved too.
Yeah. And then, all right, there's a sci-fi movie bit here somewhere. You said not just citizens. So the AI is hungry and demanding we feed it.
I'm glad you picked up what I was dropping there.
this is yeah. There's a good bit coming off of that one probably, but the AI is hungry.
Yeah. George Jetson's robots are
Yeah.
gonna want more power.
And
I'm glad you
it
didn't
must
say
stay-
Keanu Reeves. That would be really bad, though, right?
there is kind of a Matrix play
Matrix.
there.
That was the movie.
Yeah.
Yeah.
There is some Matrix. Yeah. Lots of batteries. They wanted power. And they must stay cool. Their power must be cool, right? That's a lot of solid state drives that collect a lot of heat, don't they?
Yes. Yeah. Everything. I mean, I'm looking around at your room. You have nothing but high harmonic loads and just build them just alone.
Right.
Yeah. LEDs. I
Yeah.
mean, they're wonderful, but from a perspective, they have lots of third, fifth, seventh, odd harmonic additive components that just wreak havoc on magnetics and other things like that.
I know I'm not following you, Joe. So what happens? What with the LEDs and the harmonics?
So LEDs are nonlinear loads. Okay.
Okay.
Solar, and the reason I'm able to work in that space is because in wind and solar, we're nonlinear as well. We have a pulse width modulated device, usually an IGBT, that switches up. We filter it the best we can, but you're not always able to filter it. So variable frequency drives, LEDs and everything like that, they have to have drivers to go with them. They also reflect back to the utility through transformers, high harmonic components. So 60 hertz is what we run on in the United States. But 180 hertz would be the third harmonic. So magnetics are designed to absorb. You've seen the right-hand rule. You have current going one direction. You have flux and other things. I'm going too much, but they saturate the core of transformers and they cause heating. So back to heating, we try
the
to.
harmonic does because you can't filter out all of it.
You can filter out all of it.
Oh, you can filter out.
You can filter out all of it.
But we don't.
Not everybody does. You can
Okay.
you can put active harmonic filters in places to do that on a wind turbine or a solar farm. We're able to tune that filter because we know the OEM, that is, knows the switching frequency and everything. But if you have a building like this, you don't necessarily know. If you're going to put in a notch filter, for instance, you don't know how to tune that. You don't know how many millihenries to buy. I mean, you can get close. You can approximate it. You can say, I got so many 6-pulse drives in here. This is what I'm going to do. But you can put an active harmonic filter in. It does it real time. So it looks at the line current, and it says in real time, oh, I have a third harmonic that's 12% THD, total harmonic distortion. So it injects back onto that something 180 degrees out of phase to cancel it out. So the same principle that we use for noise canceling headphones is the same principle that works for active harmonic filtering cancellation.
Oh, that's really clever. I didn't know how those fancy earbuds worked. Just loved them.
I know.
So, okay, your example on the building, so we could do that calculation today, but then tomorrow Jacob says we need different lights in here and buys different equipment. The formula just changed, right?
Bingo.
Yeah. So it's not controlled quite as much. What's the repercussion of all of this distortion?
Repercussion would be overheating. Now, if you're oversized on your transformer or your conductors, feeders, things like that, it's not a big deal. But in the wind and solar space, when you specify a transformer, for instance, are you really considering what they call the K factor that should be involved with that? So K factors are how transformer OEMs make transformers specifically designed for certain harmonic content. So like a K factor, I can't remember if it's a 1 or a 0, I forget the baseline, would be what you would consider for a traditional linear load. Linear loads are going to be resistive. They can even be inductive. It doesn't matter, capacitive. They're just linear. They're motors, incandescent, things like that. We first noticed harmonics in the 1930s from welders, arc welders.
Oh.
So they have some pretty wicked.
Makes sense.
Yeah,
Yeah.
some very wicked current signatures, and you look at them, and so smart people started looking at that a long time ago. That was long before Bell invented the BJT in 1948 and things like that. So
BJT.
Bipolar junction transistor. Sorry.
1843?
No,
No,
1948. Yeah.
Oh, 1948.
Yeah. Don't quote me on that. This is not Jeopardy, right?
No, but I'm trying to remember. We'd like to thank our sponsors, 3S Lift, a global supplier of safety and access solutions with a focus on wind energy. Their innovative ladder-mounted single technician lift called the Climb Auto System completely eliminates the need to climb ladders up to 120 meters. And if you've ever climbed in the freezing cold of North Dakota or the sweltering heat of South Texas, you know the safety and efficiency value that this product brings to wind technicians and owner-operators. In North America, 3S has installed over 15,000 of these lifts and are installing 200 per week. If your site is still climbing, you should contact 3S Lift at info@3samericas.com to get your quote to retrofit your turbines, or go on their website, 3slift.com, to learn more. Our grid, I suppose, can handle this from the users consuming the power, but it's important that the power producing technology is filtering out the harmonics as best as possible. And you're saying that's both with electrical components and thermal components.
Thermal components, overheating is the result of harmonics on magnetic circuits or conductors. Okay. So you take a true RMS meter, you put it on a conductor, you think it's reading, 100 amps, but then you put an oscilloscope on it that can measure the full harmonic spectrum, or put a harmonic meter on it that can add up all the harmonics. When you sum them all up, it looks a lot more than that. So the conductor is saying, whoa, I'm getting a lot hotter than I thought I was. That's because the guy that designed me, or gal, thought it was 100 amps when it's really like truly 115 or something.
Okay. You certainly know what you're talking about. When it
I
comes
try
to
hard.
powering
I try
it.
hard, Adam.
You're doing good. All right, a simpler one for me. Just just for a bit of education. Just how does a solar farm create energy?
um, so very high level, you have a bunch of panels. There's different technologies there. That's not where my specialty is. Okay. So you put them in various combinations of series and parallel. Um, I'm, I probably shouldn't explain that. I mean, parallel electrically, you're connected like this, and series, you're connected like this, right?
So you're trying to take panels to achieve a certain wattage
Wattage and voltage,
and
right?
voltage.
And current. So you're trying to balance those out. So these days, modern DC systems run up to about 1500 volt DC. That would be their maximum open circuit voltage. Nominally, they're around 1270, 1340, something like
This is
that.
high voltage DC.
Technically, it is.
Yeah.
Yes, technically it is. It's high voltage DC. You are very correct, and that presents a lot of different challenges.
Right.
I like to tell people who know wind very well that as we grew the rotors, then we experienced problems. The same thing happens in solar. As you grow the DC voltage, you experience comparable issues that have to be worked through. They're all feasible. So you take all those, you put them in series parallel combinations, and then you bring them into different boxes, and they call those combiner boxes. So you'll have anywhere from like 5 to 20 circuits on a combiner box.
Okay.
Okay. So think of it like a tree. So we're starting out there at the leaves, we bring it down to a branch, and now we're going to bring it down to a main trunk coming into the tree.
And is each branch 1500 volts?
Yes.
Wow.
Because the whole combination aligns to be 1500 volts.
And you
yes.
might get 5 into a combiner box.
Yeah, 5 circuits.
This is
Five
a high
circuits.
voltage component.
High voltage component. Yep.
Yeah.
And then from there, you take it back to the inverter. So that's the way a central inverter works. There are some customers that do string inverters, where almost the combiner box functions as the inverter functions as a combiner box. So then you combine it on the AC side instead of the DC side. So there's pros and cons to that. I haven't figured out which one I like more or not, but they both have huge pros and cons, right?
So far, equal opportunity.
So
All right.
far, I think so.
That's good. There's got to be options with the growth rate.
Options are good.
Yep.
Options are really good. I mean, like one pro, for instance, of a string inverter, let's just say it's only good for 350 kilowatts. It goes down, think about it. You're not down very, very much. You can go put it in pretty quickly. It doesn't weigh a lot. So those are huge pros from an O&M perspective, operation and maintenance.
Yep. Yeah, those are huge pros. Cost to repair, cycle time to return to service,
Bingo. Exactly.
very low.
Yeah.
Yeah.
Whereas on a centralized string inverter, you have more opportunities for a single point failure, but you're only bringing in 2 conductors. So you go back to the classic Edison and Tesla debates for 3 wires versus 2 wires and all that stuff right there, right? So
Yep. Yeah. I will like to hear more about pros and cons once you have them sometime between those two. I've thought about it a lot. I built my own solar panel system on my house and with micro inverters.
yes,
I didn't even know there was such a thing. And I read about it and I went, I want that.
yes,
It made it so easy.
yes. So you went more towards the string
The
side.
string side. Yeah.
Yeah.
Yeah. To me seemed like the right, well, for a residence,
Yes.
keeps the cost down, keeps repairs down. But yeah, I wouldn't know for a utility. So pros and cons, and time will tell.
Yeah.
Yeah, time will tell. Okay, but each time there's a conversion, then there's a thermal challenge.
Yeah.
Is that where you're?
Yeah. So once you get into the inverter, that's where you start having thermal challenges. The IGBT is a brilliant device. I mean, it's one of the best inventions, in the 20th century. You take the best features of a MOSFET with the best features of a BJT, and an insulated gate bipolar transistor. So high switching frequencies, relatively low losses. So the losses have to be dissipated somewhere,
Mm-hmm.
right? And that's heat. And heat just destroys IGBTs. I mean, other things do too, but heat's usually the biggest culprit. So the biggest challenge is how do you get all that power into a box? When we were in wind, we had to fit it in a tower. So we were
Right.
quite space constrained, right? Well, solar's constrained too. They have shipping constraints.
Sure.
So we have to be very sympathetic towards, especially if you're going to manufacture overseas, how are you going to package this? So a lot of them end up looking like shipping containers for a
Yep.
reason. So when you start from that point and you work down, then you say, okay, I got to get 3,000 kilowatts out of this device. And it all goes down to the IGBT. That's where the heart of it starts, is at the IGBT. How do you package that little guy? And how do you cool it? And how do you do that? And then everything else is usually built around that. So you only have so much space to work with. And to be competitive, you want to have the same footprint. We call it power density or current density, right? So if we get the voltage up, we have a significantly higher power density. So that's really the metric that a lot of people want to go by, is how many kilowatts can we get per cubic meter?
You know this IGBT component well.
Well, no,
Yeah.
I know I wouldn't say that. No,
Well,
no.
You were telling me where it was invented earlier.
Uh,
Where and when?
I can't tell you exactly when, but
Oh.
professor at North Carolina State, my alma mater. So hey,
There it is. Shout out.
NC State.
That's
Yeah, I want to say it was in the 80s. So I came to university in the 90s, mid 90s. Took 12 semesters of my time there. And so we had a very good power electronics program at NC State. There's a lot of great schools out
still
there.
a great place to go.
Still a great place to go. Clemson, Virginia Tech, Georgia Tech are all in the area where I live. They're all great schools. So if anybody's looking at a great school to work in power electronics, those are some really good ones. Got some out here too. I mean, Stanford's always good, right?
There's a few good ones. Yeah. We'd like to thank our sponsor, Altair Energy Services, and their highly trained, expert technical staff, leveraging decades of renewable power management experience into customized solutions for everyone to meet their energy goals and contribute to a better future for all. Altair's team of hardworking, respected experts are providing full-scope, turnkey repairs, planned and unplanned maintenance, system upgrades, fully autonomous technical crews, supplemental staffing, and customized dynamic scheduling to fit your power production needs. Contact Altair at info@altairenergyservices.com and learn more about their wide range of capabilities across multiple power technologies and platforms. RCA's, I don't want to maybe get into the process, but maybe if you could tell us a little bit about the benefits, the positive piece to doing an RCA.
The positive piece is
Root cause analysis.
yeah,
Let's start with the acronym.
yeah, or some people say RCFA, root cause and failure analysis.
Oh, yeah.
There's so many different methods to do them. Whatever method you like, that's fine. I think you're going to have people come on after me that can speak to the pros and cons of different methods.
Right.
But the piece that I like to focus on is to corrective action. What can we do to put this in place? So most people are familiar with administrative controls and engineered controls. So an administrative control is the lowest form of control. I like to use the analogy that if you have a hole, an administrative control would be like telling somebody there's a hole nearby.
Right.
Whereas an engineered control would be put up guardrails around it. I like to focus on engineered controls and in this space. So let's just say there's a thermal issue. Okay. I remember a PhD thermal engineer I used to work with at a former company, and brilliant thermal engineer. And we would look at all types of cooling technologies that were really cool, right? That pun, I never mean to say it, but it always comes out.
No, electricity's got to stay cool.
Yeah. And there were all types of sophisticated ways to cool things. Phase changing technology, the thermosiphons, heat pipes, things like that. Refrigerants, different types of refrigerants and things like that. And he goes, Joe, I've been doing this a long time, and it's always a bigger pump or a bigger fan. So in essence, that's what I try to do is if it's water cooled, what type of condenser, what type of pump, or if it's air cooled, where are restrictions? Why are we not getting the air there? Do we need a bigger fan? Do we have too much, pressure? Things like that. And those are usually the cases. And the benefits are sometimes the OEM might not have, when you make something and you test it in a lab, that's great. You can do one or two, but until you get a statistical sample size, you really don't know how it's going to behave because different environments change different things, different grids, everything. And you can test, but then you'll never release to market. So the biggest test is being in the system. So I try to do the same approach with the DOEs that we talk about. If I want to introduce something, I want to, crawl before I walk, and then walk before I run, and then run. I don't want to introduce something just by one test. So that's why with the 5 customers, I want to stay focused with them and get some corrective action solutions in place that will statistically move the needle.
Right. Yeah. Design of experiment, DOE, just to clarify. You made a comment I liked. You said if you would test for everything, you'd never release a product to market.
That's true.
Right. That's important, right?
Yes.
Sometimes OEMs get a bad rap here or there when the first ones, couple years go out and there's problems to solve. But it sounds like we should be celebrating those problems because we get to continue to improve upon the design, the functionality of the power plant.
Yes, I think so. I mean, everybody likes to do ready, aim, fire. Okay, nobody wants to do ready, and nobody wants to do fire.
Right.
You got to make a decision. You got to pull the trigger eventually. But ready, aim, fire is the order that we do it in. So if you don't do something, you're never really going to learn. If you just test. So OEMs, I think, are doing a great job getting out there. This is all one big industry that we're trying to make better. I mean, that's essentially my tagline. It's, I work with them as much as I work with customers, and the end goal is truly to make it better because, AI, Bitcoin miners, everything, we're just going to continue adding loads to our utility.
The AI is going to get hungrier?
The AI is going to get hungrier.
I don't know if that scares me. Or how much it scares me. Okay, so there's this side where it's continuously improving upon technology with design of experiments, and then improve to make wind and solar all that we know it can be.
Yes.
There's the other side of the non-technology side, right, where the citizens and machines apparently want more power, but we need more humans to go in and fill these jobs, right? To work at the OEMs, to transport, to build, to design, to service, repair. All of that takes more humans. I talk about this a lot with Altair, right? You're always hiring and training, and how do you make this perpetual machine work? And finding the new ones is a bit of the challenge, and it kind of makes me think about your new book. Can we talk about it for a minute?
That you're going to put a big smile on my face.
All right,
yes,
good,
let's talk about it.
We got Wanda the Wind Turbine.
Yeah,
Wanda the Wind Turbine. What was the motivation and passion here?
All right, so I have a passion for the guys and gals that work in this industry and power generation in general. It's hard work.
Yeah,
it's very hard work. Solar, you might not have a 300-foot climb, but it's still quite the challenge. If you're working on a gas turbine, there's a lot of challenges there. There's just lots of challenges in our industry that the men and women that get up every day and do it, my hat's off to them. So there was a gentleman I had worked with a while back, was an inspiration. There's 3 characters in the book. There's Wanda, and my daughter illustrated the book, and that's why I'm so
I love that.
happy about that. When she first drew up the illustrations at him, I go, this is not really the way things look. And she goes, Padre, because I remember they call me Padre. She goes, Podge. It's like, let me do it. I know what I'm doing. She goes, and I know the kids will like it. So she took a lot of artistic liberties and things like that. And that's there because it is a salute to the people who've come before us, the people that are here today, to inspire the people of tomorrow. Because AI might get hungrier, things like that, but we're going to need people to fill these gaps.
Yep.
And there are gaps. I see it all the time. So it's really to inspire, it might come across like Bob the Builder-ish type thing, and that's fine. But it's really meant to inspire young boys and girls to consider power generation or the trades in general.
I love it. It's an angle that probably not enough of us are thinking about. How do you encourage that from a young age to daydream about one day I'm going to grow up and work here?
Yeah, you're right. You're right. And I think we owe it to, as a citizen, of this world to not just think about, what we do, but think about, what we leave behind. And, I have 4 children, 1 grandchild, 2 on the way.
Congrats.
Who knows how many I'll have, and I'm a huge genealogist. That does not mean putting Barbara Eden back in the bottle for anybody who's old enough to get the reference.
Okay.
But I study those who've come before me.
Yep.
And then I learn very quickly, there'll be a lot that'll come after us. So I'm a very optimistic person, and I want to make sure that I and the other people I work with do everything we can to leave behind, trades and wonderful things that people can come in and do. So that was the inspiration for it. And Wes helped with that. It takes place in Maine. It's an opportunity. There is a problem. Wanda's friend, Tabitha, she has a problem with her gearbox.
Yep.
And she gets sad. We have to have some elements of childhood in there. And then they remember Wes. He knows how to fix her. So he comes in and fixes her, and then they get back to fulfilling their purpose of making energy. So, hopefully kids will have, see a sense of purpose in it as well.
That's really good. I don't know if you want to read it or that's too much. Or
No. It's not too much. I'll read it very, very
Okay.
quickly. I feel like I'm reading to my grandson right now.
Yeah. Well, we'll sit here and listen.
Wanda was a big wind turbine. She lived on top of a hill in Maine. She worked to make the lights stay on, like weather like the sun and rain. Wanda also had a neighbor. She lived on the hill by the bend. Tabitha was the neighbor's name. She and Wanda were such close friends. Wind turbines make power from wind. They have quite a purpose for us. They turn and turn around all day, working hard but not in a rush. People need a doctor sometimes. Wanda and Tabitha do too. Wes the technician is the man who helps wind turbines when they're blue. Wanda and Tabitha love Wes. He cares for them with so much love. Wes climbs them to take care of them. They're so high that nothing's above. Wanda and Tabitha work hard. They love their job. It has purpose. They love to see the people smile, but sometimes they get nervous. Maine can often get high, strong winds along with lots of snow and ice. Wanda and Tabitha are tough, but one stormy day was not nice. Tabitha broke her big gearbox. The storm and snow were just too strong. Her gearbox lost a lot of oil, and everything was so wrong. Wanda was afraid for her friend. Wanda was scared and had no clue. Then she remembered Wes the tech. Wes loved them and knew what to do. Wes brought a big crane up the hill. He lifted the parts in the air. He removed the broken parts out and carefully made the repair. Tabitha is fixed and now works. She is so grateful for her mend. She is making power once more thanks to Wes and Wanda, her friends.
That's fantastic.
Thank you.
That's fantastic.
Shout out to crane operators, right?
That's right. I love that you brought it a crane. It always makes a good picture.
Remember, it's a child's illustration of a crane, right?
You're gonna have to sign that for me
I'd love
before
to.
you leave. But it encouraged me to speak differently to some of my nephews that are young. The little ones will come around, and it was just a few weeks ago they were here and we were driving together, and they were asking all about the wind turbines, and the younger one, 3, one's not running, or what do they do? And I couldn't figure out how to explain to a 3-year-old, but he's playing on his iPad. It charges your iPad, keeps your food cold in the fridge. He sees one not running. He goes, Uncle Adam, so my food won't be cold? My iPad won't get charged? We got to go fix it. I said, yes, we do. Let's go fix it.
I love it.
Yeah, no, it encouraged me to have more of those conversations, because you're right. And plenty of toys, could certainly be modeled around, this type. There's the trains, right? I don't know. All my nephews have the little trains. I forget the character, but
Thomas.
Thank you. That's the one. But you get the idea. More could go into that space. It's wonderful. So they're going to not get that one because you're signing it, but I'll get another one and read it to them.
Thank you.
Yeah, congratulations. Very cool. And you can find it on Amazon. That's where I ordered mine.
It's everywhere. I was surprised how many places the publisher put it.
Okay.
I've had people overseas tell me they can get it there too. So
very cool.
I'm happy about that.
Are they translated?
No.
All right.
No. Do you want to do that? Got to make it rhyme, right?
Yeah, I'm out. That's not my skill set. Oh, that's fantastic. Yeah, no, great book. Congratulations. And I got your motivation. You had is it a shout out to also the people that, how did you put that earlier? To the technicians and the people working, engineers, and
it is, especially the people that work on these types of machines, solar, things like that every day. They work really hard.
Yes, they do.
And they have so much scrutiny, and it's very dangerous. It's extremely dangerous work. So I have a tremendous respect for those guys and gals, and it's as much dedicated to them for the present as it is for those who are going to replace them in the future.
That's right. No, it's fantastic. They have their own thermal management challenges.
They're in the hot seat.
Yeah. Well, hot and humid, or cold and snowy and icy.
Goodness.
Yeah, of course. We'd like to take this time to thank another one of our wonderful sponsors, Padge Engineering. Padge Engineering, making wind and solar all we know it can be. Are your renewable energy assets underperforming or not performing at all? Did you expect many years of longevity and they're failing on you now? Padge LLC offers many customized, engineered products and solutions to get these assets back on track. Padge Engineering also performs root cause analysis, engineering services, procurement, and construction. Visit podge.org. That's PADGE.org. Remember Padge, making wind and solar all we know it can be. Always like to do on What's Up, I call it the career discussion, but if you could take a minute and tell us, how would I become, or how would somebody become Joe?
Well, I would say...
or how did you?
Yeah, well, being Joe, you probably don't want to do. You can ask my wife. No, but becoming an engineer, I think it's a noble career. I really do. And I got started in high school. In my calculus class and drafting class, I learned to draw by hand, believe it or not, before I started on AutoCAD. This was in the early 90s. Those two teachers said, you need to be an engineer. So I go, okay. Originally, I wanted to be a pharmacist. I'm glad I didn't do that.
Yeah.
So I went to North Carolina State. They took 12 semesters from me. If you're going to think you're going to do it in 4 years, you're not. It's going to take a lot longer than that. This was before Google, right?
Oh, yeah. Going to the library.
Going to the library. I'd spent the night there many times. I lived off campus. And then I went to work in the U.S. space program. So worked for the space shuttle program for a while, doing controls and power there. Did that for almost 6 years. And while I was there, I got my master's degree, and that's when I got licensed in the state of Florida. So that's a key component, is get licensed early. Okay, there's 2 tests. The FE test, that one you can take while you're in college, but then the PE test, take that one while you're young. If you get older, you start forgetting things.
Okay. While the information's fresh.
While the information's fresh. They
Yeah.
both take about 8 hours, and they're no joke. So study for those. And then I went to grad school. That helped a lot. It really challenged things. And surround yourself with good people like yourself. As much as you can. You want people that are going to build you up, encourage you. You want people to speak positive to you, but also truthfully to you.
Yeah.
You want people to give you clear direction. So not just getting with people that are peers, but getting a mentor. So I need to take this more seriously, and maybe get some interns for my business, and help them get on that path. Because I had some along the way, and I think that's very important.
Oh, that's great. Okay. It's hard work, but it's worth it, isn't it?
It is.
It is. What brought you from aerospace to energy? Did you go right into renewables, or was there another energy?
Right into renewables. If you remember February 1st, 2003, the Space Shuttle Columbia accident.
Yeah.
Yeah, that was a very sad day.
Yeah.
7 astronauts lost their life on that day. So our president at the time, George Bush, made an announcement that the space shuttle would be retiring. So I knew that I wanted to get back to the Carolinas, where I was born and raised, and the space shuttle would be retiring. So I started looking in the renewable space, and 2005 I started interviewing. So shortly after that, I moved to Greenville, South Carolina, and that's where I call home today.
Yeah. Lots of engineers there.
Yeah. It's like a mecca for engineers.
Yeah.
Michelin's there, BMW. Every time I go to get on a flight, I see nothing but engineers. It's just crazy how many engineers live there. Same as Huntsville, Alabama.
Oh.
Another mecca for engineers.
Well, it's a good spot.
It really is.
Yeah. Greenville's a great spot. Yeah.
Yeah, it is. We try not to tell too many people about it. A lot of people are over there, Adam.
We're gonna mute that. We're gonna bleep that out, Jacob. Yeah.
I was just teasing.
Yeah, fair enough. I think the same about my own town.
I know.
Yeah. You made a comment about mentors and the importance, and that you're looking to bring that back into Padge by bringing someone. What's the best advice a mentor ever gave you?
Oh my word.
Ooh.
The best advice a mentor ever gave me. I'm trying to. Oh, I'll.
You got it.
At the Space Center.
Oh.
I knew the center director at the time. Very well respected man. He went on to have a very good career in the U.S. space program. And I was looking for upward mobility there. I was in my 20s, and his wife said to him, "Why don't you help Joe get a job?" And he goes, "I'm pretty sure Joe can do it on his own." And that vote of confidence meant a lot to me, because he was, at the time he was the second highest ranking person there. He eventually became the first. And just that vote of confidence that you don't need my help was help in and of itself.
Encouragement.
Yes, absolutely. Yeah. And, I don't know if he even remember, and he doesn't remember that, but obviously it stuck with me.
Wow, that's a great one. I don't actually often think about the encouragement piece, but it's probably 3/4 of what a mentor is doing.
It really is.
Yeah.
We have to be cognizant of our words every day. They matter. They really do. And what we say to people goes a long way.
It does. We have to be intentional with those words, don't we?
Yeah, we can't take them back if we say something bad. And, but we shouldn't lie either. We have to speak truth and love.
Yeah. All right. That was a great piece. Don't actually get that answer. That's the first time I've ever heard that answer. Asking that question was just the encouragement. Usually it was some piece of business advice. That was wonderful. Thank you for sharing it.
Thank you.
Well, I got maybe one other. If you might just share with us, what other topics? Because we talk about how this entire industry has to work. We all have to work together. Topics or companies would you like to see on the podcast, or being, sharing their story and talking about their piece of the industry?
Well, having inverter OEMs would be good, but that's going to be quite
Tougher.
challenging.
Yeah.
Maybe some. I don't know what you do on the construction side, but that's quite a big deal, and both wind and solar. So the
Yeah.
EPCs, so engineering, procurement, and construction.
Yeah. Thank you.
So they are a very vital role, in that space, and then maybe finance. It takes money to make this work, and I don't understand all the business models, quite frankly. I get asked about them sometimes, and it's usually we forecasted this, and this, and we're not getting that. What can we do to do that? But understanding, what are the formulas used to decide, where, when, how to do something like this?
No, that's a good one. And that comes into play every year at every power plant, right? To be able to ensure you're hitting your budget, whatever the pro forma said,
Mm-hmm.
and when and how to spend the money to keep it running.
Yes.
Yeah.
Yeah. PPAs, they seem like they're magical sometimes, but they're not.
No.
There's people that spend a lot of time negotiating them.
Yeah, for sure.
Mm-hmm.
No, that's a great one. And the same thing for the folks on the O&M, operations and maintenance side, which tasks to complete and when most financially effective, right? There's not just an electrical decision.
Yes. Yeah. How you Pareto and decide what's most important for the day. So people do PODs, every morning. That's plan of the day. That could be very stressful, figuring out what are we not going to do, right?
That's right. No, it's fantastic. Joe, thank you so much for coming out to Tehachapi and What's Up Renewables podcast and sharing your story and extra knowledge.
Can I say one thing?
Of course.
I might say this has been your first podcast.
It has been the first podcast. And now I'm going to look forward to the next podcast.
Thank you.
That was fun. All right. Thanks, Joe. Take care.
Thanks, Adam.